The remarkable journey of spacecraft launches. Spacecraft launches represent one of humanity's most remarkable technological achievements. These missions involve propelling a vehicle beyond Earth's atmosphere to explore space, conduct scientific research, or enable global communication networks. From the first satellite launch, Sputnik 1, to modern interplanetary probes, launching spacecraft has been pivotal in understanding our universe. Spacecraft, a vehicle or device designed for operation in outer space. It can include satellites, rovers, crewed capsules, or interplanetary probes. Launch vehicle, a rocket designed to carry the spacecraft beyond Earth's atmosphere. It provides the necessary thrust and often consists of multiple stages to achieve the desired velocity and altitude. Reaching orbit. Most spacecraft are launched to low Earth orbit, LEO, geostationary orbit, GEO, or medium Earth orbit, MEO, for purposes like communication, Earth observation, or navigation. Interplanetary missions. Spacecraft may be launched to explore planets, moons, asteroids, or comets, requiring precise calculations to ensure they reach their target. Scientific endeavors. Missions designed to study space phenomena, such as telescopes like the Hubble or James Webb Space Telescope. Human spaceflight. Transporting astronauts to destinations such as the International Space Station, ISS, or eventually to the Moon and Mars. Objective setting. Define the purpose of the mission, for example, Earth observation, interplanetary exploration, or communication. Spacecraft design. Develop the spacecraft to accommodate its payload and mission requirements. This includes engineering components like propulsion, power systems, and thermal controls. Launch vehicle selection. Choose a rocket capable of carrying the spacecraft to its destination based on weight, size, and orbit or trajectory needs. Manufacturing and assembly. Fabricate the spacecraft and its launch vehicle. Assemble and integrate all components at designated facilities. Testing and simulations. Conduct rigorous tests, including vibration, thermal vacuum, and functional tests, to ensure performance in space conditions. Launch site transport and integration. Move the spacecraft to the launch site. Securely attach it to the rocket's payload section and integrate it with the launch vehicle. Fueling. Load propellants, for example, liquid oxygen and hydrogen or solid fuel, into the rocket. Final inspections. Perform detailed system checks for the spacecraft and launch vehicle. Countdown sequence. Initiate the countdown, monitoring all systems for readiness. This phase typically involves automated sequences to minimize human error. Ignition. The rocket engines ignite, generating thrust to overcome Earth's gravity. Liftoff. The rocket leaves the launch pad, with its trajectory carefully controlled by onboard computers and ground control. Atmospheric ascent. The rocket passes through Earth's atmosphere, encountering air resistance and gravitational pull. This phase requires maximum thrust efficiency. Staging. As each rocket stage expends its fuel, it is jettisoned to reduce weight, allowing the next stage to ignite and continue the ascent. Achieving orbital velocity. The rocket reaches the required speed, for example, approximately 28,000 km/h for low Earth orbit. Trajectory correction. Fine adjustments are made to ensure the spacecraft reaches its precise orbital position or interplanetary path. Separation. The spacecraft separates from the rocket's final stage. Activation. The spacecraft activates its systems, such as solar panels, communication antennas, and onboard instruments. Orbit or trajectory monitoring. Ground control ensures the spacecraft is functioning properly and is on its intended course. Mission commencement. The spacecraft begins its mission, such as collecting data, relaying signals, or navigating toward a planetary target. Continuous monitoring. Ground control monitors the spacecraft's health, adjusting its course or systems as necessary. Each step in this process requires precise coordination, robust technology, and extensive testing to ensure mission success. Key components and technologies of space launches. 1. Launch vehicle, rocket. Propulsion system. Provides the thrust needed to overcome Earth's gravity. Types include solid fuel rockets. Use a fixed solid propellant for simpler, reliable operations. Liquid fuel rockets. Utilize liquid propellants, offering more control and efficiency. Hybrid rockets. Combine solid and liquid fuels for balanced performance. Rocket stages. Multi-stage designs shed weight as fuel is depleted, allowing efficient ascent. Guidance system. Onboard computers and sensors ensure the rocket follows its planned trajectory. 2. Spacecraft payload. The payload is the primary mission object, which can include satellites for communication, navigation, or Earth observation. Scientific probes, designed to explore planets, asteroids, or deep space. Crewed spacecraft, vehicles carrying astronauts, such as the SpaceX Dragon or NASA's Orion. Payload fairing, a protective shell that shields the spacecraft from atmospheric forces during ascent. 3. Launch pad and facilities. Launch pad, the structure where the rocket is positioned before liftoff, includes flame trenches to divert exhaust gases. Support towers provide fuel, power, and communication links to the rocket. Control centers, facilities for ground personnel to monitor and manage launch activities. 4. Propellant systems. Fuel tanks store propellants such as liquid oxygen, oxidizer, and kerosene or hydrogen, fuel. Fueling infrastructure, pumps and pipelines deliver propellant to the rocket during pre-launch operations. 5. Guidance, navigation, and control systems, GN&C. Ensure the rocket follows its precise trajectory. Sensors and gyroscopes monitor position and orientation. Thrusters and gimbals adjust the rocket's direction as needed. Software systems autonomously manage guidance and flight corrections. 6. Ground control systems. Communication links maintain constant contact with the spacecraft and launch vehicle. Telemetry systems receive real-time data on rocket performance, altitude, and speed. Tracking systems monitor the rocket's position to ensure it follows the intended path. 7. Environmental control systems. Thermal protection protects both the rocket and spacecraft from extreme heat during ascent. Structural reinforcement ensures the rocket withstands vibrations and aerodynamic forces. 8. Recovery systems for reusable rockets. For reusable launch vehicles like SpaceX's Falcon 9, recovery systems include grid fins and aerodynamic surfaces assist in controlled descent. Landing legs enable a soft vertical landing on a pad or drone ship. 1. Rocket propulsion systems. Solid propulsion uses a solid propellant that is simple and reliable, commonly used in boosters for additional thrust. Example, solid rocket boosters, SRBs, on NASA's Space Shuttle. Liquid propulsion combines liquid oxidizers and fuels, offering precise control over thrust and shutdown. Example, liquid hydrogen and oxygen engines like the SpaceX Raptor engine. Hybrid propulsion merges solid and liquid technologies, providing some control while being simpler than pure liquid systems. Electric propulsion, utilized for spacecraft maneuvering, using ionized gases for efficient long-duration thrust. 2. Advanced materials and manufacturing. Lightweight materials. Development of lightweight alloys and composites reduces rocket weight while maintaining strength. Example, carbon fiber reinforced polymers. 3D printing enables the rapid production of complex rocket parts with high precision. Example, SpaceX and Relativity Space use additive manufacturing for engines and structural components. 3. Reusable rocket technologies. Innovations in reusability have drastically reduced costs. Landing systems. Rockets equipped with grid fins and landing legs enable controlled vertical landings. Heat shields protect reusable components from re-entry heat. Example, SpaceX's Falcon 9 and Starship programs. 4. Guidance, navigation, and control, GN&C systems. Advanced sensors and gyroscopes accurately determine the rocket's position and orientation. Real-time data processing. Onboard computers calculate flight paths and adjust as needed. Autonomous navigation. Rockets now feature algorithms for self-correction during flight. 5. Launch site and ground support technologies. Cryogenic storage and handling systems manage the storage and transfer of supercooled liquid propellants like liquid oxygen and hydrogen. Mobile launch platforms facilitate flexible launch operations. Automated systems, robots, and automation streamline payload integration and vehicle inspections. 6. Thermal protection systems. Protect spacecraft and rockets from extreme temperatures. Heat shields, ablative materials that dissipate heat during atmospheric re-entry. Thermal insulation, advanced coatings and foams shield sensitive systems. 7. Communication and telemetry. High-speed data links allow real-time monitoring of rocket performance. Global tracking networks use satellite constellations and ground stations for continuous communication. 8. Simulations and AI in mission planning. Flight simulations test rocket behavior in virtual environments before actual launches. AI and machine learning optimize launch trajectories and detect potential issues in real time. 9. Innovations in payload deployment. CubeSat deployment systems. Miniaturized satellites are launched en masse with dedicated deployment mechanisms. Orbital transfer vehicles assist payloads in reaching specific orbits after separation from the launch vehicle. 10. Emerging technologies. Nuclear thermal propulsion promises higher efficiency for deep space missions. Space elevators, conceptual, propose systems to lift payloads into orbit without rockets. Hypersonic air-breathing engines could enable single-stage to orbit SSTO vehicles. Launching a spacecraft into space is a testament to human ingenuity and technological progress. It involves a complex interplay of advanced engineering, precise planning, and cutting-edge technologies, all working together to overcome the immense challenges posed by Earth's gravity and atmosphere. From the initial mission design to the final stages of payload deployment, every step of a spacecraft launch is crucial. Key innovations like reusable rockets, advanced propulsion systems, and autonomous navigation have significantly reduced costs and improved the reliability of space exploration. These advancements not only make space more accessible, but also enable humanity to address critical challenges, such as climate monitoring, global communication, and deep space exploration.